And finally, the learning curve, I think, is very, very important. So these are all things you have to think about when you're going to do 3D picking. Now, Keyence has developed our own 3D bin picking system, and we took all of these things into account, but we also did a lot of research, and what we found out there in the market was that there were three main things that were missing in every product that we found out there in the market. So we think, and our customers thought, that these three things were really, really important. So we focused very, very intently on making sure that we really nailed all three of these. So I think you'll agree they're important. High image quality and detection capability, good ease of use, as well as easy setup and installation, connection simplicity, and with that, a complete package. So let's talk a little bit about how we've addressed those points. All right, so to start off, Keyence's 3D bin picking product is called the RB. And the RB actually comes in 4 different sizes that you see there on the screen. There's a small size called the RB500 that gives you very, very high resolution, but it has a small imaging area. And then on the right-hand side, you can see our largest model, which actually has a 1400 by 1400 by 1 meter deep imaging area. So for larger parts, this is more suitable. So we have a wide range of different heads that we can utilize. One thing you'll notice, it looks kind of like a drone. A lot of people call this the drone bin picking system. The reason is because we have 4 cameras, and these 4 cameras have to be spaced out to give a high quality image. This equipment is actually designed for random bin picking, but actually a large portion of our applications are single part pick or structured parts. So we can handle either situation. But this is the general structure of our system. There's a pattern projector in the center that creates structured light, and then 4 cameras that actually create the 3D image to then allow for us to do the 3D bin picking process. All right, so I'd like to hit on those 3 points individually and maybe highlight some of the details. All right, let's start with the image quality topic. And one thing I hate is when somebody says, hey, we got the best camera, and they don't explain why. Honestly, it's really, really simple. The simple fact that we have 4 cameras gives us a higher quality image than other systems that might just have 1 or 2 cameras combined with a structured light generator. Why is that? Well, in 3D picking, when you have randomly oriented objects, you're going to have a lot of blind spots. And having these different camera perspectives allows you to see perspectives that you wouldn't be able to see with a single camera. So the simple reality is that you actually get a higher number of valid 3D data points when using this system. Another thing to consider, many of the applications are shiny metal parts. And when you have shiny metal parts, you can create glare. Imagine if you have a projector and just 1 camera, and you blind that 1 camera with glare. In that case, you're out of luck. And since parts are randomly oriented, some of these parts are going to create glare. But if you have extra cameras, say 3 extra cameras, you can actually create a very, very high quality image. And if 1 camera gets blinded from that glare, the other 3 fill in the missing data. Each of these cameras is 4 megapixel. And what we're doing is we're actually doing 136 separate captures that actually create a single 3D image. That all happens in around a second or so. And the pattern projector occurs in the X and Y direction. So when I say we have a high quality image, it's pretty simple. It's down to these 4 cameras and this capture method. Okay, let's talk about the ease of use. Now, ease of use is a little bit intangible, right? But there are some tangible features that we've got that really make it straightforward and quick to set up and learn. So first of all, from a calibration standpoint, we have an auto calibration function, which we provide the program for your particular robot, which will automate that process. It really makes it quick and easy. Also, we can do all of our teaching of grip and place positions on our software without the robot being connected. So you don't have to wait for the robot to be delivered. You also don't have to be standing on the floor to teach this thing. You can do it from the comfort of your desk. Finally, from the robot programming perspective, we've got a couple features that really set us apart that can make your life easy and lower risk. The first is the path planning function. Path planning allows our system to determine the entire path of the robot for you, so you don't have to worry about it. We handle all of the collision avoidance and singularity avoidance. In addition, we have a picking simulator which uses a physics engine that allows you to fully test out your end-of-arm tooling prior to ever purchasing the system. So it really allows you to understand on the front end if it's going to work or not, or have a good shot of working. All right, the third point, connection simplicity. So the drone, the imager and projector you see on the left-hand side, that's all one piece and there's no moving parts. So you don't have to adjust the focus, the aperture, anything like that. You basically mount it above the work cell and every adjustment inside is electronic. You then connect that to one of our vision system processing units. This is a very common product. There's 60, maybe 80,000 of these out there in the US. And this is dedicated to image processing and does not use a PC. So you don't worry about OS updates or anything like that. That then connects directly to the robot controller. And I'll go over some of the different brands we work with, but we actually provide the code that manages that communication. So we very much eliminate the finger pointing that often exists when two vendors are trying to interface with each other. All right, let's talk about some of the key features. First, let's talk about detection performance. If you look at that bin on the left-hand side, one thing you're going to notice is those parts are very thin and very shiny. So they do create glare, and for many systems these are difficult to detect reliably. If you look at the 3D image on the right-hand side, what you're going to notice is that there are a high number of valid 3D data points. What's a valid 3D data point? Any area that's not black. So you'll notice outside of the bin and on the walls, you're getting a lot of invalid pixels. But down there in the corners and on the parts, you can see that it's a very, very complete, high-quality image. And that's down to having those 4 cameras. On the right-hand side, maybe a little bit hard to see, but there are actually little notches at the 12, 3, 6, and 9 o'clock position on those parts. They're very small as a percentage of the part as a whole. However, we have the ability to assign something called a key feature region, which allows us to better clock that part once we pull it out. And it may allow us to avoid having to have a 2D camera connected, which will then do an offset. That being said, that is an option, and I'll go over that later for our system. Okay, I mentioned before that imaging can be a challenge for 3D picking. If you have shiny parts with flat surfaces at an angle, you can actually project the pattern onto adjacent surfaces, which can cause problems. We actually have a feature that actually helps with this called multi-reflection suppression. Honestly, a lot of people don't need to use this, but it's good to have in that toolbox just in case. So we have this feature that can help you if you need it. Another feature that can help with difficult imaging scenarios is HDR, high dynamic range. Those of you who are familiar with vision systems or photography might know that HDR allows you to capture at 2 different shutter speeds. In this case, what we can do is combine the 2 images together to get a higher quality image. This is another feature that most people don't need to use, but when you need it, and it's good to have in the bottom of the toolbox just in case. All right, so let's look at some videos. We'll start at the one on the left-hand side here. Those are those parts being picked. You can see that we are picking with suction. We are doing full collision avoidance on that wire basket. We're finding the wire basket and actually also presenting to a 2D camera at the bottom of the screen. And then we're doing a fine position offset before we place that part. Now you'll see the flashing in between each capture. That's the 136 separate pictures that are being taken. Now let's look at the one on the right. If we look at the video on the right-hand side, what we're going to see is that those parts are being picked from that stack, and those parts are very thin and very shiny. Notice how consistently those parts are being placed. The upper right-hand corner, you can see that the boundary is very effectively extracted. That's down again to the 4 cameras. We also can separately tune our boundary and our surface search algorithm portions, which can actually allow us to get a better result for this. This is actually very, very difficult, and I don't know of other folks who can do this type of application. All right, let's move on to the setup. Now, one thing I mentioned before is that we have an auto calibration feature. I'm going to show you a video in just a second. But before I do, I actually want to go over the different robot brands that we interface with. Now, everyone that you see in this list, we actually have auto calibration available for. Now, if you're not in the list, it's okay. It can still be possible. We just choose custom in that case. But I think you'll see most of the usual suspects here, right? Fanuc, Yaskawa, Kawasaki, Kuka, ABB, UR. Fanuc is the most common for us to work with. In the US, it's probably the most prevalent brand and you know, therefore the most common that we're working with. But all of these are ones we work with on a regular basis. All right, so let's take a look at the calibration and how it works. So this is a video from one of our labs. And what we're doing is actually executing the auto calibration process. We're driving our calibration target around to 27 different points and recording the position of it. Then at the end, what we're going to do is actually rotate around the tool center point. And when we do that, we're actually able to infer the position of joint 6. After this process, we know exactly where in space the robot is compared to the vision system. So this can be very useful as a time saver, especially when you're going to be handing this process over to someone who may not be a robot expert. All right, so let's talk about place position registration. On some systems out there, you actually have to teach a place position that matches with every pick position. And if you have 50 pick positions, this can get very, very tedious. On our system, you only have to teach a single place position for each search model that you teach. So it can be a big time saver. So let's watch a video of these parts being picked. Notice we're picking from a different spot each time. And what I'm also going to do is I'm going to try to pause it right when it's taking a picture. See if we can get it on the next capture. Okay, so it's a little bit hard to see, but you can see the stripe pattern that occurs right down the lower right-hand corner. Again, 136 pictures are being taken during this second or so period of time. We figure out the place position despite the fact that there are many, many pick positions taught on the system. Okay, let's move on. In a moment, I'm going to go into our software and actually show you nearly from start to finish how to set our system up. But before I do, I'd like to cover again 2 key topics that I mentioned before, because they're really important and really valuable in terms of shedding risk. So let's talk about the path planning and the picking simulator. What things do you have to worry about? I mentioned a whole list earlier in the presentation, but if you're a robot programmer, you've got to worry about whether the robot's going to hit things in the environment, whether the tooling's going to hit things, and then after you grab that part, especially if they're long parts or big parts, you got to worry about them hitting things in the environment. So there's a lot of things to worry about. And then when you're designing the machine, what do you have to worry about? Well, is the robot size correct? Have you put it in the right place? Is the container suitable? How about the aspect ratio of the container? If it's too deep, it can be very difficult to get down inside of. Probably the biggest variable that you got to think about is the end of arm tooling. The reality is that you don't really know if all this is going to work together until you build it. And by the time you've done that, you've invested a lot of time and money. So there's a lot of risk there, right? What if it doesn't work and you spend all that money? Okay, so let's think about that. while we're thinking about these two features. Path planning is going to allow our system to determine the entire path of the robot for you, so you don't have to worry about it. We make sure that no part of the tooling, the product you're picking, or the robot itself hits anything in the environment. This allows you to also very quickly handle all the constraints getting down inside that bin. The picking simulator actually allows us to create a virtual bin of parts that are randomly oriented using a physics engine, and then we can go through and build the program on our software and then fully test it. Again, you can do all of this before you ever buy a robot or ever build anything. So this is a huge, huge risk mitigation feature. All right, so let's get into the software. Before I do, here's a simulation running. And this is actually pretty difficult, right? We have an obstacle on the corner. We've got a bin that's fairly deep and narrow, parts that are randomly oriented, and we're getting down inside that bin all the way to the bottom and then placing those parts onto that little pedestal. So this is actually the simulator running in our virtual environment. Okay, so what I'd like to do now is actually show you how our software works. This will only take maybe 6 or 7 minutes. So let's go ahead and get back into it. This is actually our CVX software. So what we're going to do is start by clicking Set Camera, and then I'm going to go over here and choose a model. Now I'm going to actually use the mid-size RB800 model for this demo. One cool thing we've got is this auto-tuning button, and this auto-tuning button actually allows us to place a bin of parts under the camera, and then when we click that, it's automatically going to figure out the optimal shutter speed for us. All right. Next stop, set robot connection. So what I can do now is choose my robot manufacturer. You'll see the same list you saw a moment ago. And what we're going to do here is choose FANUC. The reason I'm choosing FANUC is because I happen to have down here a robot model for FANUC already loaded into the system. We'll click Edit and Import, and then I can load in this FANUC robot model data. This is an M10ID8L. Downloaded this from our website. We're going to do full collision avoidance and path planning on this robot. So let's click Close. And the next step normally is going to be calibration, but I'm not actually connected to a robot right now, so there's not a whole lot I can do here, but you saw the video, so I think you have an idea of how this works. Let's go ahead and move on. I'm going to now click the simulator button, the picking simulator button, and this will allow us to actually build a program. And there are other ways you can get through it too, but everything actually is located under this menu, so this is one option. When I click that, it actually gives me this 3D viewer, and this 3D viewer is actually what we're going to use to see the process. So what I'm going to do now is go in and click Import CAD Data. All right, so let's click Import CAD Data, and I'm going to actually load in this shaft holder, which is our part. We'll click Open, and then we can choose the units, which are going to be millimeters. We'll click OK. All right, this is the part we've just loaded in. That should look familiar. It's from that video you saw a few minutes ago. We'll click OK. Now it's loaded in. Great. Okay, now we're going to choose the number of objects that we're going to throw in that bin. Let's choose, I don't know, maybe 220. We'll click OK and generate single image. All right, there we go. We are now populating that. Uh-oh, too many parts. Okay, I knew that was going to happen. But I really wanted you to see our physics engine at work. All right, 220 is too many. We'll probably dial that back to 20 to kind of keep things going. But I really wanted to highlight how this does a great job of randomizing these parts. I was skeptical at first, but I'm now sold on this. Okay, let's click Abort, and let's go back to maybe 20 parts to kind of keep things moving along. All right, 20 parts. Great. Image generation completed. We can now move on to our object detection tool. Okay, Without doing anything else, we already are identifying all these parts in the bin. And what you'll notice is that there's some markings on these parts. So for example, this part right here, it says 8D96. So this is part number 8. It's a 96% match, and it's actually face D that's been identified. Now, what is face D? Where did that come from? Well, the system automatically, when I load the CAD data in, figures out that there are X number of faces that are suitable to teach picks on. In this case, there's 6. And we've got A, we've got B, we've got C, and D. That matches what you see right there. We also have E and F. So we can teach pick points on any of these faces. All right, let's go down to Picking tool now and show you how we actually set up the picking. So we're going to start with primary settings. We'll start by creating an object model. Now I'm just going to click Generate Model here. The reason this step is in here is because our system has the ability to not only use the CAD data, but to also, excuse me, also use an image that we actually capture with the system. Okay, so let's continue. Now that we have this image in our system, we'll click Close, and we will go down here to Hand Settings. This is where you can create a hand model. So we'll go in here and actually click Add, and I can actually load in CAD data for my end of arm tool. So if I've designed a gripper or downloaded it from a website, I just click Open, and then I choose my units. All right, there's our tooling. This is what we're going to use, and I can adjust a variety of things on this. I can actually add cuboids and cylinders as well, but in this case, all I'm going to do is actually move my tool coordinates away from joint 6 down here to between the fingers. So this is where we do that. Alrighty, we'll click OK. There we go. And now we will go to the next step. All right. Now we're going to actually teach some picks. So how do I do that? I click RIP registration, and we'll zoom in here. You'll notice that we have A, B, C, D, E, and F. Okay, so you'll also notice that we've already taught picks on all these places. It's because I cheated. Not really, I just don't want to bore you by showing you on all 6 faces. That being said, I will show you how I taught at least one of these so you know how it works. All right, so how do I replicate this grip we see right here? All I do is I click Add, I click Grip Registration, register by clicking on the image, and then I can click anywhere on this 2D representation of that face. So right here maybe, that crosshair is then stored, the X, Y, and Z position of it. Now we'll click Z Fit to Object. All right, great. Drops it down and matches the tool coordinates with the crosshair. All right, when you look at that part, you may be thinking, hey, that part is circular. Can I teach picks all the way around? And the answer is yes, and it's very easy to do. So we can actually rotate around the Z-axis. Now, see that blue dot? That's actually our axis of rotation. And I don't want it to be on the tool center. I want it on the part center. So I'm going to actually move that over about 1 inch. All right, great. Now what I can do is choose an angle range. In this case, I'm going to choose plus or minus 130 degrees. And then I have an angle interval of 10 degrees. And what I've just done, everybody, I've taken that original pick and copied it 26 times. The system automatically will figure out which of these are viable picks, and throw out the ones that aren't, and pick the most efficient ones. So teaching many picks is very quick and easy to do. All right, so What I'm going to do before I proceed is actually enable all the grips that I taught before, just so we can use them. And now we can move to the next step, and we are almost ready to run this thing. All right, the first part is already identified in the bin right there. And you'll also notice that a path is already generated, and that path is automatic. But some parts of that path need to be specified by the user. For example, the place position. Okay, so number 5. How do we place that part right there? Well, let's go in and edit those coordinates or that place position. We go into place position registration. All right, you'll notice A, B, C, E, and F already taught. But D is not taught. That's the one we just did together. So let's teach that one. Click Edit. Go into Search Model. We'll choose a reference grip position. I'm going to choose the one that we taught together. That's this one. Click OK. Then what we're going to do is actually zoom out. Now, if I'm not connected to a robot, I'm going to need to actually jog this robot around virtually. So I happen to know where this needs to be. So I'm going to move this joint 1 over maybe 50 degrees. And I can also enter robot coordinates directly or jog these directly. Again, I know exactly what these need to be, so I am cheating a little bit here, but you get the idea. All right, so if we're happy where that's being placed, we can go ahead and click Register. This can be adjusted later if we need to. All right, great. So now that's stored. Anytime I pick from the D face, I'm going to place it exactly like this. All right, so we are about ready to run this thing. I'm going to click Next and Done a few times and get to the top menu. And now comes the fun part. We get to run this thing. So I'm going to click the Execute button and watch what happens. On the left-hand side, each part will turn red before it gets extracted. You'll notice adjacent parts will fall into place and readjust. The path will be updated in the center of the screen each time, although it's not going to change very much because this is actually a pretty shallow bin, no obstacles in the way, pretty easy, honestly. On the right-hand side, there's a capture stored every time we created an image. So you can always go back and rerun if you've changed the program. Now, on your first run through, you're guaranteed you're going to have some parts that didn't get picked. Now, these parts don't look so hard, right? All right, we got 90%. Well, what was the problem here? Well, we don't have to guess because we have a tool that actually helps us understand what went wrong. So I click Check No Good Cause, and let's zoom in and see what's going on with this part. All right. So this is the part we're looking at. I could also look at the other part, like this. But notice that I can see all the possible picks that were taught. And there's maybe 70 or 80 of them there. I have all these problems, and it tells me what they are. Collision with the bottom of the box, collision with the side of the box, object collision, all these different problems. None of them worked. And that part's pretty easy. Okay, so what can we do here? Well, I can see that actually the C face is sticking up. So I can zoom in and see what's going on. All right, so I see that actually I was not very thorough when I taught my C face. I got 2 picks there, 180 off from each other, and very clearly we are hitting the side of that box. How could we fix this? Well, we could probably teach a pick on this side and grab that part. So watch how fast we can do this. We just click Close, Picking Tool, Edit, go to C, click Add, Grip Setting Navigation, register by clicking on the image. I'm going to click up here this time instead of down here. Go to the next screen, Z Fit to Object. We have just taught the pick. Now let's go test it. Click OK, done. Now, when I click Execute, we'll see if that part is extractable. Hopefully it'll turn red. Great. Okay, now we're 95% there. However, we've still got this part that we can't get. All right, so we can go through the same process again, but honestly, sometimes a part will be in an orientation where you can't grab it. So if you're in that situation, we have some unique features that allow you to get out of that situation and deal with it. So this is actually the end of the programming portion. So hopefully you enjoyed that. But I'm going to show you a couple videos now that show you how you can deal with these difficult part orientations in a very elegant way. Okay, so we are going to go ahead and pop up the current screen. And we have these features called departure settings. This describes what we do when we can see the part, but we can't get it out. Well, let's go ahead and take a look at these videos. Okay, here's the first one. You may notice that that part corner is under this horizontal member. If I try to pull that straight up, it's going to get stripped off, but watch this. Did you see that? We just checked a box in our software, and we actually pulled that part out of the way before we lifted it up. And not that fancy, but it's a very simple and easy thing to do with our software. Here's another example. Parts can be overlapped and get stripped off like this. Big problem. However, our system actually has the ability to identify this situation and automatically move parts over. So watch this. We see the part, we slide over, and then we pick. Here's another example. Cylinders get stuck in corners where you can't grab them with fingers. This is very common with fasteners, so watch what we can do. No pickable parts right now, but we can do this. This is a secondary operation called a slide. It only executes when there's no valuable or valid picks. Now we can go back, re-image, and grab the part the way that we really need to. And one last example, same part you just saw in the software. Let's say we want to grab it from the face that's up against the wall. We can't do that, right? So we're out of luck. No valid picks right now. But we can still use our slide operation because we can see that part. Now let's give it a shot. We go down, make contact with the part, move over. Hopefully we move it, and then we can re-image and grab the part the way that we want to. This isn't a silver bullet. It doesn't solve every problem, but it's a much more elegant way of stirring a bin or avoiding operator intervention that has to be manual. So this can be a very, very valuable feature. Okay, so last point. Most people are curious if they have an application, how do they move forward and test it out and see if it's going to work? So Keyence has a headquarters in Chicago, Illinois, and in that headquarters we actually have a robot lab where we have multiple robot brands, and we are actively doing testing. So customers on a regular basis are sending us bins of parts. We're recording videos of the picking process. We're also doing simulations, just like you saw a few moments ago. We'll record videos of those simulations and then send them to you. You can also visit this lab virtually or in person if you'd like. If you do decide to go forward, the equipment is all stock, available overnight, and we will do a design review with you to make sure you're not overlooking anything. We do offer vision programming training and assistance. We offer virtual training for free once a month. We do have training videos and setup guides, phone and email support during business hours, and on-site as needed. One thing we have found is that actually a lot of support can be provided very quickly via screen sharing. So we've found that this is actually a very, very effective tool in terms of helping customers in remote locations. Anyway, I appreciate your time, and we're going to move on to a Q&A session. Thank you very much.
All right, thanks, Rob, for that great presentation. I was really impressed by one of the early videos that showed the picking and the alignment of those thin metallic plates. I worked on a similar problem earlier in my career, and I can attest that all those problems you mentioned, like glare and edge detection, are really difficult to solve. And so using a 4-camera solution probably would have made my life a lot easier.
Yep. Everybody knows glare is a big problem for machine vision, right? So
Yeah.
anything you can do to help with that is definitely nice.
Yeah. So we've already got several good questions, and there's still time for our audience. So if you want to submit more questions to Rob, please do so. But Rob, let's jump into the questions that we do have. The first one is asking is, what is the typical cycle time for bin picking?
That's a good question. And it actually is very, very application dependent. I think a lot of people will actually focus on how much time it takes the camera to generate the path or generate the pick point. But the reality is that the bulk of the cycle time actually ends up being in the robot motion for most applications. So I would say an average for us, it usually takes maybe 1.2 seconds or so for the imaging and maybe another second for the path generation. But the point is we can actually bury that into the robot motion time. So once you've done your first pick, you can then image as soon as the robot's out of the way and then be ready for the next one. The reality, though, is that most random 3D picking applications are not running that fast. Typically, they're going to be slower than 5 seconds or so. What you have to keep in mind is that there's a lot of variables. I mentioned this earlier in the presentation. It's not just identifying the picks and then going and picking the part. You've got to think about the physics of the end of arm tooling. You got to think about, well, what happens if the part gets stripped off the gripper? What happens if parts get intertwined or interlocked? What if you have a mispick? What if the part falls off? There's so many things that have to be considered. So it's generally good to be careful and exercise a healthy amount of caution when you're thinking about cycle time. So definitely something to watch out for. It's not a simple answer. Thanks for that question. That's great.
Yeah, and I think following up on that is that one image or one video where you stopped and was it showing that pipelining process where the robot had moved out of the way, and while it's still placing the part, you were imaging the bin.
That's correct. Yes.
Okay.
Yeah. So the acquisition's really fast. It's just you have all these potential complicated robot motions that have to occur when you get to the bottom of a bin and maybe the part's in a complicated orientation. You got to get all the way down there, and sometimes that can take longer for the robot motion side. So it's something you definitely have to think about.
Sure. All right. The next question we have here says that you mentioned we can use the software for free before buying a system. How does somebody get that software?
Yeah, another good question. So full software licenses come with the system. However, we actually have trial versions of the software that are 2 or 3 weeks, I believe. And those can be downloaded from our BinPick support page or our website. So if you're interested, you can feel free to reach out to me. Actually, if you email binpicksupport@keyence.com, you can get to our BinPick support group and they can help with this. Or you can also email me directly if you want, which would be rob.halasz@keyence.com, spelled HALASZ. You could also just go to our website and a chat box will pop up and you can just ask for me and they'll get it to me. But yeah, we'd love for people to try it out. Sure.
Excellent. And I would think even for people that have moved past that trying out phase, that are getting ready to purchase systems and install them, having the ability to do that physics-based modeling and everything while, say, you're waiting for your arm to come and all that assembly can really reduce your time to deployment.
Yeah, it certainly can. And maybe more important than that, it allows you to understand if the application is going to work or not, or have a good shot of working. And, waiting, time is money, but after you spend the money, if it doesn't work, that's even worse, right?
Yes, indeed it would be, yes. So this question is asking how many of these systems are currently in use?
I get this question a lot, actually. It's in the thousands. I can't give exact numbers, but definitely in the thousands. Keyence is actually a pretty large company. Actually, Keyence and Fanuc are very similar in size. And we have maybe 1,200 salespeople in the US at this point. And this product is actually handled by our entire machine vision system team, which is over 100 people in the US. So it's a pretty wide installation base, both in the US and worldwide.
Okay. This one of our viewers asked, are the various manipulations like the slides and all that information that you're pulling directly visible to an API so that you could separately control the program and dynamically command the arm kind of at that level?
That's a good question. So yeah, sometimes people request the ability to have a high level of adjustability and control over it. It is not, you can't control the slides externally. However, what you can do is inside the software, you can actually set priorities to the particular slides and so forth. So it is possible, if you want to set up a slide, to make it so it always happens only if you don't have any picks, or maybe you have another operation that occurs before you ever do a slide. So there are some ways that you can customize it, but you can't do it separately from outside of our environment.
Okay. All right, this question is looking at kind of the higher level. It's comparing 2D versus 3D vision for this robotic guidance. And 3D obviously has lots of advantages, which you covered many of them here, but there's also some people worried about it's more challenging in setup. Are there cases where 2D might still hold an upper hand, or has 3D just become so easy that 2D is kind of moving away?
I like this question. Okay, this is becoming much more common for us to see. Kind of the question between, should I use 2D or 3D? So I like to put things in buckets. Let's do that. So there's the applications that are clearly 2D, and it's obvious that you should go 2D. And then there's the ones that are clearly 3D. So clearly 3D might be like random bin picking. The parts are clearly randomized. If we go back to the 2D bucket, parts that are flat and they're laying on a flat surface, they're not overlapped at all, right? So those are the easy decisions. But the ones in the middle, the bucket in the middle is, hey, you could do either one. And how do you decide? The reality is that 2D cameras, the hardware is cheaper, right? And it's much more readily available. More people have experience with it. So I think a lot of people want to default to that. But there's a lot of situations where people are trying to hammer square pegs in round holes. So for example, let's say that you want to pick up washers that are maybe laying on top of each other on a flat belt. Okay, can you do that with 2D? Yeah, you can probably image those and find them. And maybe with the vacuum gripper, you can go down and get them. Maybe you use a distance sensor on the end of arm tooling. There's a lot of smart engineers out there that can make something like that work. However, the amount of engineering time that goes into that and into the troubleshooting can quickly overcome the cost savings that occurred by going with the inexpensive hardware. And think about all the things that could go wrong, right? You have a washer that's metal, it's at the wrong angle, the light hits it the wrong way, you don't detect it quite right. All sorts of variables exist. And I'm an engineer, I hate variables, right? I want as few variables as possible. So, that's what 3D gets you. It helps you kind of hold these variables constant. So there's actually a whole list of things that 3D helps with for an application that's borderline. So whether it's these washers that are overlapped, or maybe it's, let's say it's stacked brake rotors and one of them might slide off and be at an angle or something like that. It's like semi-structured. So think about this. You've got lighting. Lighting's a huge variable. If you're using 3D, if you're using structured light like you're using on the RB, then you don't really worry about the interaction between the ambient light. You've got a structured light pattern that's going to basically get you the height data. So you don't worry about the intensity. So it takes that kind of problem out of the equation. Here's another one. How about distortion? If you've got parts that have maybe cylindrical depth, what you can have is, as you get towards the edge of the field of view, you're going to actually start to see the sidewall of that cylinder. and then you can have error in detection because of that. I guess maybe another thing is grip registration. So if you're using our software with the 3D, you can actually do all the teaching in the software. But if you're using 2D, you've got to do it manually. You've actually got to bring the robot down and teach it manually. And I guess one other thing is hand collision judgment. So you may remember from the presentation that our system actually does the collision avoidance of the entire robot arm and the end of arm tooling. So that's something you don't have to worry about in this case. But if you're using 2D, you still got to worry about collisions and so forth. And maybe one final thing is, how do you know if you're pulling the right part, the part off the top and so forth? So that's maybe another reason that 3D is better. All those things are, I think, things that most people don't really think about. They get kind of blinded by the difference in cost because 3D costs more.
Yeah.
So we've realized and noted that. And as a result, we actually released a special order. That's not special order, actually. We keep them in stock, but we have a special controller that actually deletes the path planning and actually allows us to just use the 3D pick portion of the system. And we can actually offer that at a more attractive price, actually bringing the gap closer together between 2D and 3D. So I'm sorry, I gave a lot more information on that answer than you probably wanted to hear, but the bottom line is it's worth considering 3D because the cost difference isn't as much as it used to be. And there are a lot of benefits.
Well, and that goes back to that you need to think about the whole system and the lifetime of operation. The cost of just that hardware at the beginning is not the only cost you're going to run into.
Of course, absolutely.
Yeah.
Absolutely.
All right, this question here says, the communication interface for the larger control system with PLCs, which Keyence supplies this module, can you explain what sort of data from the camera is useful to the larger system? So I'm not following that, so maybe you can rephrase it for us.
Sure. So I think probably what they're referring to is we have our control module that you saw in the demo earlier, right?
Mm-hmm.
So we don't use a PC. We have a controller, and it's the same controller that's used for all of our vision systems. So I don't know. There's probably 100,000 of those out there in the U.S. right now. So that device is dedicated to image processing and so forth. And because it's also used for our normal vision systems, it has all of the I/O that you would normally have available for those systems. So anything that you're generating from the program can actually be output. So for example, if you want to output a count or any pass-fail criteria, you could do that. You can here's a common one actually. People want to know when they're close to the bin being empty. They want to get a signal out for that.
Mm-hmm.
So that's another signal that could be used. I think I mentioned before that we have a direct connection between our controller and the robot controller. We're connecting via TCP/IP, so there is a direct link back and forth. So you normally don't need another device like a PLC to make this thing operate. However, you can, at the very same time as you're connected to the robot, you could be connected via Ethernet IP to a PLC, and then you could actually be interfacing with other devices in the environment, which is not uncommon. So hopefully that answers that question. I think it probably does.
Yeah, I think so.
Okay.
It helped me anyway, so that's good.
Good.
This question is, for 3D vision, do you need to be aware of any special networking considerations to accommodate that you're getting more data so you can react as live as possible between the camera and the robot controller?
Okay. Yeah. So if you remember earlier on, we were taking 136 pictures very, very rapidly. So you saw the flashing occurring in the video. What happens is in our system, we actually are compiling all of those images inside the head and then making the 3D image before we ever send it off to our controller. So rather than having to communicate all those individual 136 images down to that controller first, we only have to create the 3D image and then send that down. So the nice thing is that happens very, very rapidly, and we don't have to worry about that time frame. The other factor, of course, as we mentioned, is that a lot of the time constraints are based in the robot motions. So all of that can be occurring, while we're doing these other things, right? So hopefully that answers that question. Our controllers actually are very, very fast. As I mentioned, they're not PC based. So they have individual processors that are dedicated to specific processes in the system. So it allows the controller to work very, very rapidly. And it also makes it so that we're not worried about any resource conflicts or anything like that that might normally occur in typical systems.
Very good. Well, it looks like we've got all the questions that come in so far. While we wait a minute to see any other questions come in, Rob, is there anything
Yeah,
else you'd like to elaborate on or make sure the audience takes away from your session?
yeah. I mentioned this before, right? When we talk about bin picking, it's shiny. It's a technology that people get excited about, and it makes sense why they get excited, because they see the potential for cost savings, and also it's really, really cool. But the problem is when people get excited about things, they make emotional decisions, and as I mentioned before, it can be dangerous. There's a lot of things to look out for. So what I want to make clear is that we're not interested in selling systems for applications that don't work. And one thing I've learned over the past 25 years is when you sell something that doesn't work, you're going to have a lot of communication with that customer, and it's not going to be the kind of communication that you'd like to have. So we're very interested in successful applications, and we, as much as you, the customer, want to see these be successful. Our system is very, very quick to deploy and allows you to do so with the lowest amount of risk of any system out there. So before anybody goes forward with an application, we want to help them understand how it's going to work, do full testing. So if you're interested in testing out an application, send us an STL file. We can do a simulation for you. If you want to ship parts to us, we're happy to run tests on those parts and show you what we honestly think about it. And if it's borderline, then we'll talk about it and make sure everything's really clear and on the table. So yeah, we'd love to talk to anybody, and we'll be honest with you about whether we think it's going to work or not.
Excellent. Well, thank you, Rob, for that great presentation and the great discussion
Of course.
during this Q&A. It was a pleasure talking with you.
Thank you. Enjoyed speaking with you as well.
All right. Before we wrap up, I'd like to announce our giveaway winners for this session. 2 winners will receive an event t-shirt and 6-in-1 multi-use screwdriver, courtesy of Mauser Electronics. Congratulations, Jamie McGinnis and Patrick Napolitano. We'll be in touch with you after the event to ensure we have the information we need to send you those gift packages. Thank you for attending Control Automation Day 2024. I encourage you to check out today's other live sessions, keynotes, and published content. You'll be redirected in just a moment to Keyence's booth page where you can browse and access their other content. Thank you.